Amid the harsh deserts of the Middle East, where there's nothing but rocks, wind, and burning sun, the people of Israel achieved something that stunned the world. They carved more than 12,000 kilometers of canals through the desert to create a massive artificial river, channeling billions of liters of water from the Mediterranean Sea to sustain an arid nation. But Israel took it even further. They turned all that seawater into fresh, drinkable water using cutting-edge technology inside massive desalination plants. Curious how this almost unreal process actually works? Join Mandarin Tech as we dive into the story behind one of the most extraordinary engineering feats of our time. For decades, the Negev Desert in southern Israel was practically a dead land. Dry, cracked, and almost impossible to cultivate. Summer temperatures soared above 110 degrees Fahrenheit. Rain fell only for a few weeks each year, and underground aquifers slowly dried up with every generation. Agriculture, the lifeline of this young nation, stood on the brink of collapse, while many families survived on water hauled in by trucks from faraway regions. Amid this unforgiving landscape, just a few dozen miles away, lay the Mediterranean Sea, vast, endless, and filled with salt water. That contrast sparked Israel's boldest gamble, to pull the sea inland, deep into the heart of the desert. The Desert Water Project was officially approved in 2000, with an investment of nearly $3 billion. With that level of commitment and vision, Israel didn't just turn seawater into life. It challenged the desert itself, forcing rivers to flow through the sand. Before a single drop of water could be channeled, the first task was to turn the hard, barren desert into a workable construction site. They began with high-resolution satellite imagery, ground-penetrating radar, and thousands of wind measurements to map the shifting dunes and identify areas stable enough for construction. Survey teams lived in the heart of the Negev Desert for months, drilling hundreds of boreholes, some more than 100 feet deep, to study the geological layers hidden beneath the sand. Every route marker was placed by hand and recorded with centimeter-level accuracy. The entire canal alignment had to avoid the wind corridors, where a single sandstorm could bury the whole worksite overnight. Hundreds of bulldozers were deployed to flatten the dunes, cutting down the high ridges and redistributing the sand into lower areas. The goal was to create a smooth, balanced surface strong enough to support construction machinery without the risk of collapse. Each section was carefully scraped and leveled under strict supervision, with surveyors checking elevation and slope to ensure uniformity across miles of open desert. Conveyor systems pushed the excess sand away from the work zone, while compactors gently pressed the top layer to form a firm and workable foundation. After the bulldozers had leveled the dunes, the sand still needed to be stabilized. Engineers discovered that injecting water into the loose surface helped bind the grains together, creating a denser and more cohesive layer. Using long sprinkler arms and underground pipes, they sprayed controlled amounts of groundwater across the site, allowing moisture to penetrate several inches deep. Once the sand reached the right level of dampness, heavy rollers moved in, compacting the surface to remove air pockets and lock the particles in place. The constant rumble of steel drums echoed across the desert as each pass of the roller turned soft, shifting sand into a firm, uniform base. By the time the surface dried under the desert sun, it had hardened enough to carry the weight of cranes, mixers, and supply trucks. A solid foundation built from nothing but sand and water. Once the groundwork was complete, hundreds of excavators and massive dump trucks began one of the largest digging operations ever undertaken in modern Israel. Every day, around 70,000 tons of sand and soil were removed from the Negev Desert, along a construction corridor stretching nearly 250 miles. Over 1,200 engineers, operators, and laborers worked in rotating shifts, enduring daytime temperatures that often exceeded 115 degrees Fahrenheit. The canal was shaped with a wide U-profile, about 150 feet across at the base and an average depth of 23 feet. To allow water to flow naturally without pumps, the longitudinal slope was held within 1 inch per 100 feet, an incredibly tight margin over such distance. Survey crews rechecked elevation with laser leveling instruments every 160 feet to ensure the canal floor stayed perfectly aligned. Most of the excavated sand was reused to build up both sides of the embankments, forming levees 10 to 16 feet high. In hilly terrain, bulldozers cut the layers step by step, while in low-lying areas, trucks hauled and stabilized fill material until the grade was reached. In weak soil zones, engineers drilled 16-inch sand piles up to 20-25 feet deep, or mixed cement and clay to strengthen the base and prevent subsidence. The construction site stretched for hundreds of miles, dotted with concrete batching plants, mechanical workshops, and field engineer camps. Under the scorching sun and swirling dust, long convoys of trucks and machines moved endlessly, a mechanical river carving the shape of a real one into the heart of the Negev Desert. This excavation phase lasted for months. In the Negev Desert, the challenge wasn't just the heat and dryness, it was the thirst of the sand itself, capable of absorbing any exposed water within hours if the canal bed wasn't properly sealed. That's why the lining phase became one of the most critical stages of the entire project. First, the canal bed and slopes were moistened and leveled with a 2-inch layer of fine sand. Then concrete panels about 4 to 5 inches thick were poured into sections measuring 16 feet long by 10 feet wide, each separated by expansion joints. These joints were filled with hot bitumen sealant to prevent seepage and allow thermal movement. In areas with unstable subsoil, an additional HDPE geomembrane layer was placed beneath the concrete, fixed with steel anchors and covered with a protective sand cushion. Altogether, more than 220 miles of canal were lined with concrete, making it one of the largest waterproofing systems ever built in the Middle East. Along the embankments, engineers planted vetiver grass and desert acacia to stabilize the slopes and minimize sand drift. From above, the canal appears like a shimmering silver ribbon cutting across a sea of gold, a concrete artery waiting to carry its first life-giving water through the desert. A massive canal can't simply be a trench for water. It requires hundreds of auxiliary structures to ensure transportation, flood control, and proper water regulation. At the head of the system, engineers from WAPDA built the head regulator at the Townsa Barrage, where water from the Indus River is diverted into the canal through 9 enormous steel gates. Along the main route, there are more than 900 different engineering components, including reinforced concrete bridges, spillways, siphons, drainage culverts, and aqueducts carrying water across natural streams. Whenever the canal intersects a road or railway, a new bridge is constructed to maintain traffic flow. In sections that cross natural waterways, cross-drainage structures are installed, large conduits that allow the natural flow to pass beneath the artificial canal. In addition, distribution gates are placed every 6 to 9 miles to control water flow into secondary branches. Everything must operate in perfect harmony because a single malfunction, whether at a gate or an aqueduct, could deprive hundreds of hectares of farmland of their water supply. After more than 15 years of construction, the entire canal finally entered the water testing phase. Engineers opened the gates at the Townsa Barrage, letting water from the Indus River flow section by section, gradually increasing the discharge from 500 to 2,000 and then 6,000 cusecs. Along the route, technical teams inspected every point, measuring pressure, checking for leaks, monitoring the canal slopes, and recording any ground movement. Every deviation was corrected before the system was fully opened. When the first rush of water flowed through the cracked, dry canal bed, the regions of Darabugti and Jalmagsi erupted in celebration. Locals called it the day the desert came back to life. Wherever the water reached, cheers followed. It wasn't just a flow of water, it was a flow of hope. The fulfillment of a dream generations of farmers had waited their entire lives to witness. The moment real water finally ran across their land. The water from the Mediterranean finally makes its way through the artificial river that cuts across the desert, but it can't reach people just yet because it's still seawater, and in the desert, salt can be even more dangerous than drought. Before becoming a source of life for millions, it must pass through an intelligent desalination system, a chain of advanced technologies stretching from the coast deep into the inland. Here, seawater goes through multiple stages: mechanical filtration, sand settling, oil separation, and then nanofiltration and reverse osmosis, RO, where every salt molecule is removed, leaving only pure, drinkable water. Digital sensors constantly monitor salinity, pressure, and flow, automatically adjusting the process to maintain the highest level of purity. Only after passing all these layers of control does the water enter the main canal, beginning its hundreds-mile journey across the Negev Desert. No longer seawater, but a true lifeline for an entire nation built on hope and resilience. The pretreatment stage may have already captured large debris and sediments, yet seawater still carries countless fine particles and microscopic organisms. To prevent these from clogging the heart of the technology that follows, a phase of fine filtration is introduced. Inside massive filtration tanks, black hollow fiber membranes act as ultra-thin barriers, blocking algae, bacteria, and even the tiniest remaining particles. The initial filtration stages are only the beginning. The decisive phase unfolds within the reverse osmosis system. Under immense pressure, seawater is forced through semi-permeable membranes, each pore hundreds of times smaller than a strand of hair. This invisible wall allows only pure H2O molecules to pass through, while salts, heavy metals, and trace chemicals are left behind. High-pressure pumps generate tens of bars of compression, transforming the salty, murky mix into a stream that's nearly pure. Yet as it leaves the RO modules, the water is so pure it becomes almost empty, and that very emptiness must be corrected. Precise dosing systems add small amounts of calcium and magnesium to rebalance pH and restore a clean, natural taste. Next comes disinfection. Ultraviolet light, or ozone, eliminates any remaining microorganisms, while a trace of chlorine ensures long-term safety through the pipelines. Every parameter is monitored in real time, and lab samples are analyzed constantly. Only when all standards are met is the water pumped from storage tanks into the distribution network, flowing through miles of underground pipes to homes, hospitals, and factories. It is a complete cycle where the salt of the ocean is transformed into safe, drinkable water, a testament to the remarkable power of modern technology. When the first flow of water crossed the Negev Desert, everything began to change, not just on the surface, but deep within people's lives. Land that once cracked under the burning sun started to come back to life. Farmers who had once left because of drought returned, pitching tents, driving stakes, and plowing the first fields of their lives amid the sand and rock. Water from the main channel of the national water carrier was divided through a network of secondary canals, pressure pipes, and drip irrigation systems that delivered it directly to each plant. A technology Israel itself invented to save every drop of water as precious as gold. The project began in 1953 and took over 11 years to complete, costing around 420 million Israeli lira, equal to hundreds of millions of dollars at the time. Once operational, the system could transport up to 72,000 cubic meters of water per hour, bringing fresh water from the north all the way down to the Negev. As a result, regions once thought hopeless were revived into thriving agricultural zones. In the early years, tens of thousands of acres of farmland turned green. Where there was once only dust and sun, now stood orchards of oranges, vineyards, wheat fields, vegetable farms, and rows of date palms heavy with fruit. Seen from satellites, a long green ribbon winds across the golden desert. The green artery of Israel, the artificial lifeline connecting the north and south of the country. The transformation went beyond the fields. Villages were rebuilt, children had schools, and high-tech farms rose from the sand. In the heart of the lifeless Taklamakan Desert, a railway more than 2,000 kilometers long cuts through billions of tons of sand. a project that made even American engineers take notice of China's determination. It's a feat that cost President Xi Jinping's government over $3.5 billion and required more than 12,000 workers across a full decade to complete, now standing as one of the greatest symbols of modern engineering. But how did they manage to fight through fierce sandstorms and scorching heat to turn that sea of desert into the world's longest railway network? Join Mandarin Tech as we uncover the story behind this extraordinary achievement. For decades, China's northwestern region, Xinjiang and the Tarim Basin, remained a blank space on the national map, a vast, isolated land split by two massive mountain ranges and the Taklamakan Desert, which covers more than 127,000 square miles. In summer, surface temperatures can exceed 160 degrees Fahrenheit, while in winter they can drop to minus 13 degrees Fahrenheit. There's no water, no electricity, and beneath the feet lies nothing but shifting sand, no solid foundation to build upon. Yet hidden beneath that unforgiving sea of dunes lies billions of tons of untapped energy and minerals, oil, coal, and most notably, rare earth elements, the materials considered key to global technological dominance. To unlock these resources, China had no choice but to undertake what was once called an impossible mission, building a railway across the desert. So the Hotan-Rokiang Railway was built, 890 kilometers long, as part of the Taklamakan Desert Loop, a 2,685 kilometers circular railway network running along the southern edge of the desert. Completed in June 2022, it is the longest desert railway in the world. Before a single bridge or rail was built, Chinese engineers faced a question that seemed impossible. How do you choose a route across a landscape that never stops moving? They began with high-resolution satellite imagery, ground-penetrating radar, and thousands of wind measurements to determine prevailing wind directions, dune movement, and zones with relatively stable ground. Survey teams spent months living deep in the desert, drilling hundreds of boreholes, some tens of meters deep, to study the layers beneath the sand. Every route marker was placed by hand and recorded with centimeter-level precision. The line had to avoid the wind corridors where sandstorms could sweep away entire trains, yet remain close enough to access oil and coal fields along the Tarim Basin. This was the very first step in turning what was once a blank, white space on China's map into a steel curve wrapping around the desert. Before construction could even begin, hundreds of local farmers were called in to tackle a task that seemed simple, but would decide the project's fate: anchoring the sand. They bundled straw, dry twigs, and thin bamboo into long sheaves, then planted them into the ground in a checkerboard pattern. Each square measured exactly 1 square meter and was arranged diagonally at 45 degrees instead of straight lines. This layout broke the wind's direct flow, scattering its force in different directions and forcing the sand to settle within each grid. Under a blistering heat of more than 140 degrees Fahrenheit, the farmers pressed each bundle deep into the soft dunes and covered it with an extra layer of twigs to make it hold. The first few grids quickly spread across the horizon, forming thousands of organic sand fences that stretched all the way to the farthest dunes. After several months, these straw checkerboards blanketed hundreds of acres, turning the once shifting desert into a patchwork of golden brown and green. The sand stopped moving, the ground hardened, and heavy trucks could finally drive without sinking. On this newly stabilized foundation, the massive desert construction could finally begin. After the sand surface had stabilized, the next challenge was to reshape the terrain. Hundreds of bulldozers were deployed to flatten the dunes, cutting down the high ridges and redistributing the sand into lower areas. The goal was to create a smooth, balanced surface strong enough to support construction machinery without the risk of collapse. Each section was carefully scraped and leveled under strict supervision, with surveyors checking elevation and slope to ensure uniformity across miles of open desert. Conveyor systems pushed the excess sand away from the work zone, while compactors gently pressed the top layer to form a firm and workable foundation. After the bulldozers had leveled the dunes, the sand still needed to be stabilized. Engineers discovered that injecting water into the loose surface helped bind the grains together, creating a denser and more cohesive layer. Using long sprinkler arms and underground pipes, they sprayed controlled amounts of groundwater across the site, allowing moisture to penetrate several inches deep. Once the sand reached the right level of dampness, heavy rollers moved in, compacting the surface to remove air pockets and lock the particles in place. The constant rumble of steel drums echoed across the desert as each pass of the roller turned soft, shifting sand into a firm, uniform base. By the time the surface dried under the desert sun, it had hardened enough to carry the weight of cranes, mixers, and supply trucks. A solid foundation built from nothing but sand and water. After the surface had been compacted, workers began spreading a base layer of soil over the stabilized sand. Dump trucks poured out loads of reddish earth, which bulldozers then pushed and leveled across the area. This layer added weight to the sand below, strengthening the surface and keeping it from shifting under heat or vibration. Each section was evenly spread and compacted, forming a dense, stable base strong enough to support the first stages of construction in the desert. Once the ground base was fully stabilized, workers began erecting the bridge pillars. To build them, they had to drill through dozens of feet of loose sand until reaching the solid gravel or compact soil beneath. Reinforced concrete pile drivers operated day and night, using steel casing pipes and bentonite slurry to keep the boreholes from collapsing. Concrete was poured from the bottom up through tremie pipes to prevent air pockets, while the steel cages were positioned with millimeter precision. Even the slightest misalignment could cause the pile to tilt or lose stability. Because daytime and nighttime temperatures differed by more than 130 degrees Fahrenheit, construction crews worked mostly at night, when the wind was calm and the sandstorms eased. Thanks to these steel and concrete piles, the railway's foundation seemed to grow roots deep into the desert. On top of those foundations, 11,000 bridge piers began to rise, row after row, forming a vast concrete forest stretching across the desert. Each pier stood between 16 and 50 feet tall. The shafts were cast using slip-form molds, reinforced with galvanized steel and salt-resistant additives to withstand the desert's corrosive climate. The short, uniform spans between piers were designed to minimize the effects of wind and extreme temperature changes. As the sun set behind the Kunlun Mountains, the endless lines of pillars stretched toward the horizon, a skeleton of steel and concrete unshaken by the desert winds. On top of those pier caps, thousands of pre-stressed concrete box girders were lifted into place using heavy crawler cranes or self-launching gantries. Each girder was over 100 feet long and weighed several hundred tons. They were transported on specialized flatbed rail cars and hoisted one by one onto the piers. Engineers then aligned the girders with laser precision, keeping tolerances within just a few millimeters. Once the spans were secured, crews poured the bridge deck slabs or installed precast concrete panels, forming a smooth surface for the tracks. Every span was spaced to allow wind to sweep freely beneath, carrying drifting sand away so it could never bury the line. More than 65% of the Hotan-Rokyang Railway, about 310 miles, runs on these elevated viaducts. From above, the railway appears like a silver ribbon cutting across an ocean of gold, a living monument to human ingenuity against one of Earth's harshest landscapes. Next, these concrete blocks being installed are called sleepers, or railroad ties. They're placed evenly along the track bed to hold the steel rails in position and distribute the weight of passing trains. Workers align each sleeper precisely, then use a lifting frame to lower the rails onto them. Once fixed and fastened, they keep the track straight and stable, preventing it from bending or shifting under heavy loads. A crucial step before the trains can safely run through the desert. After the sleepers were secured, crews began laying the steel rails on top. Each rail, stretching more than 260 feet long, was lifted into place by specialized cranes and carefully aligned along the center line. Workers adjusted every joint and gap to allow smooth expansion under heat, then tightened the fastening clips that locked the rails onto the concrete base. It took 11 months of continuous work to complete the hundreds of miles of track stretching across the desert. When the final bridge span was completed, the entire line entered the testing phase. Engineering trains ran up and down the route to measure settlement, vibration, rail temperature, and wind-induced sway. The bridges were load-tested with trains weighing thousands of tons. Results showed elevation deviations of only a few millimeters, even after hundreds of test runs. Thanks to the elevated design and natural airflow beneath the viaducts, no sand accumulated on the tracks. All operational data flowed to the control center through IoT sensors and solar-powered cameras that monitored every section in real time. After 6 months of rigorous testing, the Hotan-Rokiang Railway officially opened in June 2022, completing the 1,685-mile loop that circles the Taklamakan Desert. Along with the railway, China also built a highway that cuts directly through this vast desert. The Tarim Desert Highway, considered one of the most ambitious infrastructure projects in Western China. It was constructed to link the two oasis cities of Luntai and Minfeng, stretching for more than 300 kilometers across the desert's core. Work began in 1993, and the highway officially opened on October 4, 1995. After just over 2 years of construction under harsh conditions, shifting dunes, violent sandstorms, and searing heat that reached over 122 degrees Fahrenheit. The project cost an estimated 1.75 billion yuan, or roughly $260 million. Beneath its asphalt surface lies a multi-layer foundation of gravel, straw mats, and geotextiles designed to stop the drifting sands from bearing the road. Today, the Tarim Desert Highway not only connects isolated solar farms and scientific research outposts, but also acts as a passage for ecotourism, leading travelers through what was once among the most inhospitable landscapes on the planet. To power both the desert highway and railway, China installed a massive solar panel system across the region. This area receives more than 2,700 hours of sunlight each year, ranking among the highest in solar radiation anywhere in the world. Instead of letting the scorching sun continue to burn the sand, engineers turned it into a vast source of renewable energy. Along the Tarim Desert Highway, which stretches for more than 436 kilometers, they built 86 solar-powered pumping stations. Each station is equipped with hundreds of photovoltaic panels, generating electricity to pump groundwater from depths of over 100 meters. That water is then carried through an underground pipeline network and distributed using drip irrigation technology, allowing more than 200,000 trees along the highway to survive in a region that receives almost no rainfall. As a result, the Tarim Highway has become the world's first carbon-free desert expressway. A place where sunlight generates electricity, electricity produces water, and water sustains life. In Taklamakan, solar energy does more than power streetlights or run water pumps. It sparks hope for environmental renewal. Once known as the Sea of Death, this desert is now becoming one of the world's largest ecological laboratories, a place where sunlight, technology, and human determination come together as one. And as transportation became more accessible, tourism in the desert began to thrive. Along the edges of the Taklamakan and Gobi deserts, vast man-made forests, solar farms, and water reservoirs have been developed into parks that combine scientific research with tourism experiences. In some regions, community-based tourism is growing, blending ecotourism with the Uyghur and Mongolian cultural heritage. Travelers can join camel riding tours that cross the desert, lasting anywhere from 2 to 5 hours depending on the route, passing over rolling dunes like ocean waves and stopping at rest areas set up in the middle of the sands. Each trip costs between $40 and $120 US. By combining conservation, education, and real-world experience, the Taklamakan Desert today stands not only as a symbol of ecological restoration technology, but also as proof that humans can live in harmony with nature. In just a few weeks of conflict, a sea passage less than 33 kilometers wide managed to squeeze nearly 20% of the world's oil flow. That place is the Strait of Hormuz, the most critical energy corridor on Earth, where more than 20 million barrels of oil pass through every day to keep industries running from Asia to Europe. But the real epicenter of the panic does not lie only in this narrow choke point. It lies in the massive machine being blocked behind it, Ras Tanura. Far beyond the idea of a typical export terminal, this mega infrastructure is essentially the largest steel master valve of the global energy system. A super export hub where up to 6.5 million barrels of oil per day are pumped directly from deep beneath the Saudi desert and loaded straight into some of the largest oil tankers on the planet. Let's join Mandarin Tech to explore the energy heart of the modern world. If the surface of the ocean is an open transportation network, then Strait of Hormuz is the most brutal spatial trap in the global energy system. On a map, it looks like nothing more than a narrow water passage between Iran and Oman. But in reality, for major energy powers such as Saudi Arabia, Iraq, Kuwait, and the UAE, this is the only gateway through which their black gold can reach the world. The dominance of Hormuz has worried Gulf countries so deeply that they have been willing to spend billions of dollars just to create an escape route. The clearest example is the 380-kilometer ADCOP pipeline, worth about $4.2 billion US, built by the UAE across the desert to bypass this shipping route. Engineers even once proposed an extraordinary idea, blasting through millions of tons of limestone and cutting across the 2,000-meter-high Hajar Mountains to build the Musandam Canal, creating an alternative outlet to the open sea. But all these technical efforts proved ineffective. The billion-dollar pipeline can carry less than 1/10 of the total flow, while the mountain-cutting canal has remained only a concept on paper. This reality confirms a harsh geopolitical principle. Hormuz is a bottleneck that cannot be broken, and no man-made mega infrastructure on Earth can truly replace it. And the worst-case scenario is unfolding right now. Since late February 2026, military tensions between Iran and the coalition led by the United States have turned the Strait of Hormuz into one of the most dangerous hotspots in the world. After airstrikes targeting Iran's anti-ship missile systems near the strait, Tehran responded by warning that it could close the shipping route and by deploying military measures to control maritime traffic. Within just a few days, oil tanker traffic through Hormuz dropped by more than 90%. Hundreds of vessels were forced to wait outside the Gulf, and many major shipping companies temporarily suspended operations due to security risks. Missile responses, drone activity, and warnings of possible attacks on commercial ships pushed the maritime corridor that carries about 20% of the world's oil supply into a state of partial paralysis. As a result, oil prices rose above $100 per barrel, marine insurance costs increased several times over, and energy supply chains from Europe to East Asia began to face clear pressure. In this situation, the world has begun to recognize a troubling reality. When Hormuz becomes unstable, no economy remains safe. And behind that narrow bottleneck, where some of the largest oil reserves on the planet are concentrated, the entire Gulf export system is also starting to face an unprecedented logistics crisis, with the central focus being Ras Tanura port. Hidden along the eastern coast of Saudi Arabia and facing directly toward the Persian Gulf, Ras Tanura port is not simply a seaport. It is the largest oil export terminal on the planet, where millions of barrels of crude oil from massive desert oil fields are gathered, pressurized, and pumped straight into the ocean every day to sustain global industry. Beyond that, it is a vast coastal industrial complex directly connected to a trans-desert pipeline network stretching thousands of kilometers, ultra-high-pressure pumping stations, enormous storage tank farms, and offshore loading piers capable of receiving some of the largest oil tankers ever built. From here, supertankers of the VLCC class can carry up to 2 million barrels of oil per voyage as they depart the port and head toward major consumption centers across Asia, Europe, and North America. In 1939, construction of the first pier structures at Ras Tanura port officially began. However, before the access bridge could extend toward the offshore loading area, engineers first had to build a protective offshore breakwater. At that time, the eastern coast of Saudi Arabia lay on a shallow seabed covered with thick layers of soft sediment, frequently disturbed by seasonal winds and waves in the Persian Gulf. Without a protective barrier, large oil tankers could not safely approach the loading zone. As a result, a multi-layer rock-filled breakwater was selected as the most suitable solution for the offshore construction conditions of that period. The breakwater was built by placing a core layer of dumped rock using barges, followed by larger rock layers to improve slope stability. An outer layer of heavy armor stones, installed by floating cranes, helped dissipate wave energy and reduce seabed scour. At the same time, the navigation channel was dredged to provide sufficient depth for safe tanker access. As soon as the water inside the breakwater became stable enough for offshore construction, engineers at Ras Tanura port began building a key structure, the oil export causeway extending out to sea. This causeway created a direct connection between the onshore pipeline network and the offshore tanker loading area. The main challenge came from the seabed conditions along the eastern coast of Saudi Arabia, where thick layers of soft marine clay made it impossible to place structures directly on the seabed, like at typical deepwater ports. Instead, the causeway was supported by large steel pipe piles driven deep into stronger load-bearing layers beneath the seabed using offshore construction barges. After the foundation system was completed, steel girders and connecting frames were installed span by span, forming a long technical corridor from the shoreline to the offshore loading zone, allowing crude oil to be transported directly from inland desert fields to large tankers waiting offshore. By the mid-1950s, crude oil exports through Ras Tanura port increased rapidly, and the North Pier was no longer able to meet operational demand. At the same time, the arrival of new generations of oil tankers with deeper drafts required loading infrastructure to extend farther into deeper offshore waters. In response, Saudi Aramco began constructing the South Pier as a dedicated offshore loading complex designed for large-capacity tankers. Unlike the nearshore causeway structures, the South Pier was engineered to withstand much higher mooring forces and vessel impact loads. Its foundation system used large-diameter steel pipe piles, driven deeper and arranged at higher density to ensure stability under wave and wind conditions typical of the shallow Gulf waters. Mooring dolphins and breasting dolphins were positioned separately from the main platform to reduce direct structural loads during berthing and tidal movement. Multi-joint marine loading arms were installed on the offshore platforms to connect directly with tankers, allowing high-volume pumping while accommodating vessel motion. At the same time, the offshore approach channel was dredged in seabed elevations, adjusted to ensure safe access for large tankers under different tidal conditions. As the number of oil tankers increased rapidly with rising global energy demand, a single loading area was no longer sufficient to maintain continuous flow at Ras Tanura port. The problem was not simply expanding one large terminal, but creating multiple offshore loading points operating in parallel in the Persian Gulf. To solve this bottleneck, Saudi Aramco developed the Sea Islands complex as independent export points, allowing multiple oil tankers to operate at the same time without interrupting flow. The Sea Islands were formed by dredging and pumping sand from the seabed to create artificial offshore land masses, then reinforced with rock layers to stabilize their shape and prevent erosion. Beneath these islands, large-diameter steel pipe piles were driven deep into load-bearing layers to support the entire loading platform structure. The system was divided into breasting dolphins, mooring dolphins, and loading platforms to distribute the forces generated when multiple tankers operate simultaneously. On the loading platforms, multi-joint marine loading arms maintain stable connections under wave and tidal movement, ensuring that oil flow remains uninterrupted during operations. At the same time as expanding its offshore loading points, Saudi Aramco constructed a massive crude oil storage complex behind the port terminal to ensure continuous export flow management. The cylindrical steel storage tanks typically have diameters ranging from about 60 to more than 100 meters, with each tank capable of holding between 500,000 and 1 million barrels of crude oil. These tanks are arranged in a network directly connected to the central pipeline system. The tank foundations are reinforced with compacted sand bedding layers and circular concrete ring foundations to evenly distribute the enormous loads generated by the stored oil. The tank shells are assembled using a staged plate lifting method, allowing fast and accurate construction under the harsh coastal desert climate conditions. Above each tank, floating roofs are installed to reduce oil evaporation and minimize fire and explosion risks, ensuring safe operation for the entire large-scale storage system capable of holding tens of millions of barrels at Ras Tanura port. To transport crude oil from the onshore storage tank area to the offshore loading complex at Sea Islands, Saudi Aramco constructed a large-scale subsea pressure pipeline system that serves as the main transmission route of the entire export hub at Ras Tanura port. This system allows millions of barrels of crude oil per day to be transported directly from onshore processing facilities to offshore loading points serving very large crude carriers. The pipelines are made from large-diameter, thick-walled steel pipes designed for long-term operation under high-pressure conditions and in highly corrosive seawater environments. Before installation, individual pipe sections were continuously welded together on specialized pipe-laying barges and then inspected using ultrasonic testing to ensure sealing integrity and structural strength. The outer surface of the pipelines was coated with concrete weight coating to increase stability and keep the pipeline securely positioned on the seabed. During installation, the pipeline was continuously lowered from the laying barge through a curved support structure that controlled the bending radius, helping reduce stress as the pipe made contact with the seabed. Prior to installation, a trench was prepared along the pipeline route to protect it from ship anchors and seabed currents. After placement was completed, the pipeline was backfilled with protective material, forming a stable energy transport corridor between the shoreline and the offshore export terminal complex. To reach black gold, engineers operate massive drilling rigs that penetrate several kilometers deep beneath the deserts of eastern Saudi Arabia. After each drilling stage, steel casing pipes are lowered and special cement is pumped into place to strengthen the well walls, creating a stable production corridor through high-pressure geological layers. Few people realize that the oil exported through Ras Tanura port actually begins its journey deep underground in giant fields such as Gawar and Abqaiq. Here, oil does not exist as large underground lakes as many imagine. Instead, it is trapped inside tiny pores within reservoir rock, similar to water held in a sponge. After the wells are completed, oil flows to the surface using natural reservoir pressure or enhanced recovery methods such as water, gas, or steam injection to maintain stable production. Even with modern technology, typically only about 30 to 40% of a field's total reserves can be recovered. From the production wells, crude oil is transported to primary processing centers where gas and water are separated, then sent through pipeline networks stretching thousands of kilometers across the desert toward Ras Tanura. There, massive storage tanks act as logistics buffers before export. Finally, high-pressure pumping stations push the oil to offshore loading terminals, such as South Pier and Sea Islands, where VLCC tankers receive millions of barrels per loading cycle, supplying energy to East Asia, Europe, and North America. In the global energy industry, not every country with oil holds the same level of power. Real energy power belongs to countries that not only have massive reserves, but also the ability to deliver that oil to international markets every day at an industrial scale. Saudi Arabia is one of the few countries that meets both conditions. Today, the countries with the world's largest oil reserves include Venezuela, Saudi Arabia, Canada, Iran, and Iraq. Among them, Saudi Arabia stands out for maintaining stable export capacity for decades. The giant Gawar oil field alone has produced millions of barrels per day for generations. However, reserves only become real power when they can be transported continuously to global markets. To make this possible, Saudi Arabia built a vast energy logistics network, including thousands of kilometers of desert pipelines. Major processing centers such as Abqaiq, and especially Ras Tanura port, the country's main oil export gateway. Ras Tanura handles about 90% of Saudi Arabia's hydrocarbon exports and can ship roughly 6.5 to 9 million barrels per day. Its strategic location is also close to the Strait of Hormuz, where around 20 million barrels of oil, about 1/5 of global supply, pass each day. Because of this, Ras Tanura is not just a coastal terminal, but a critical junction linking desert oil reserves, cross-desert pipelines, and one of the world's most important maritime energy routes. Every year, hundreds of massive ships, up to 1,000 feet long and weighing more than 40,000 tons of steel, carry out the final voyage of their lives. But instead of docking at port in glory, they run straight onto the muddy beaches of South Asia, where thousands of small workers stand waiting, with only a 5,400 Fahrenheit cutting torch and wages of less than $4 a day. Here, these floating cities that once crossed the oceans are cut apart into pieces, each steel plate, each ship compartment, each pipeline, until they vanish as if they had never existed. More than 90% of a ship's materials can be recycled, but the price paid is a hazardous working environment. In this journey, join Mandarin Tech as we explore the place where every ship ends, the ship-breaking industry, the process of dismantling massive structures, and the lives of workers who are trading their own lives to rebirth steel for the world. To understand why massive ships must be scrapped, first look at the entire life cycle of the maritime shipping industry. At present, the global commercial fleet includes more than 100,000 vessels. Each year, around 2,700 new ships are built and launched, while 400 to 500 older ships are retired from service. A ship operates efficiently for about 25 to 30 years. After that point, maintenance costs rise rapidly. The steel hull gradually deteriorates due to saltwater corrosion. Cargo holds, machinery systems, engines, and even the hull structure can no longer maintain their original level of safety. In addition, global emissions standards require ships to reduce sulfur content in fuel, making many older vessels legally obsolete. Beyond economic and technical factors, there are also sudden reasons that force a ship out of service: collisions, groundings, fires, or severe mechanical failures. When repair costs exceed operational value, dismantling becomes the only option. And a crucial question emerges. Where do these ships go? Are they dismantled at sea in complex salvage operations involving cranes, robots, and structural simulations? Or are they towed straight onto land, heading for the beaches of South Asia, where labor is cheap, coastlines are wide, and demand for scrap steel is enormous? The reality is that when a ship reaches the end of its life cycle, its final destination is very likely to be one of the three most famous ship-breaking yards in the world: Alang in India, Chittagong in Bangladesh, and Gadani in Pakistan. Together, these sites account for nearly 70% of global shipbreaking activity. In Alang, hundreds of ships are driven directly onto a shoreline stretching about 6 miles each year, forming a massive open-air dismantling assembly line. Chittagong is known for its beaching method, forcing ships onto muddy shores using the full power of the tides. Gadani was once the fastest ship-breaking center in the world, though it came with significant risks. Despite their differences in scale and technique, all three share the same role: stripping apart tens of thousands of tons of steel and feeding it back into the global economy. Before a ship is dismantled, it must first be valued. The buyer, typically scrap steel traders or shipbreaking companies, assesses the vessel based on two main factors: the amount of recoverable steel and the current market price of scrap steel. A typical cargo ship can generate between 3 and 6 million US. Cruise ships are worth even more because they contain large quantities of non-ferrous metals, stainless steel, and expensive interior equipment. The purpose of ship dismantling generally falls into two categories: breaking the ship for scrap and dismantling it for component reuse. Most of the steel, copper, aluminum, electrical cables, propellers, shafts, and machinery systems are recovered. Meanwhile, valuable components such as engines, navigation equipment, Hydraulic pumps and generators are carefully removed, inspected, and resold to smaller vessels or local markets. In this way, before a ship is officially cut into sections, it has already completed its final economic role, becoming a source of raw materials and components for many different industries. After the final inspection and completion of the sale paperwork, the ship prepares to enter the last journey of its life. It is no longer capable of moving on its own, so a team of tugboats takes on the task of towing it into the scrapping yard. The critical moment always takes place during the few hours of high tide. The rising seawater lifts the massive hull, creating enough depth for the tugboats to control the direction and thrust, allowing the ship to slide deep onto the sandy beach. If the calculations are wrong, the ship can become stuck offshore or drift off course, creating major difficulties for the entire operation. But when everything goes according to plan, the ship moves onto the beach under its own momentum and comes to rest there. As the tide recedes, the hull settles firmly into the shoreline, exposing the enormous underside that has remained hidden beneath the water for decades. This is the moment that marks the transition. From a vehicle of transportation, it becomes a mass of material waiting to be dismantled. In the months that follow, hundreds of workers will move through every steel compartment, dissecting the ship from the inside out. The first stage is to completely empty the ship's compartments. Workers begin dismantling the interior: doors, tables, and chairs, lights, stainless steel railings, decorative panels, electrical wiring, and ventilation systems. Each item is inspected to determine whether it can be reused or resold. For cruise ships, this work is far more complex. Areas such as theaters, cinemas, gyms, swimming pools, bars, and hundreds of cabins must all be stripped manually. Many valuable components, such as industrial kitchens, sound systems, and air conditioning units, are removed intact and sold on the market. Once the interior layers are removed, the environmental handling team takes over. They pump out residual oil from the tanks, treat sludge, wastewater, and any chemicals remaining in pipelines and technical tanks. This is an extremely critical step. Even a small amount of flammable gas or uncollected oil can turn the flame of a cutting torch into an ignition source. After everything is cleaned, the ship is left with only an empty steel framework, ready for the heaviest stage, cutting the hull. Cutting the hull is the core task of the entire process. Workers erect scaffolding, mark the cutting lines, and begin using oxyacetylene cutting torches hotter than 3,000 degrees Celsius to pierce steel plates nearly 3 centimeters thick. Each completed cut separates a steel section weighing several tons, which is carefully rigged with cables before being dropped onto the sand by gravity. The sound of steel hitting the ground always echoes. Another part of the ship's body has been severed. Tractors then drag these large sections deeper into the yard to be cut into smaller pieces. 3 teams of workers, steel cutters, transport crews, and cable recovery teams work continuously to recover as much material as possible. Depending on the size of the ship, this entire stage can last from several months to more than a year. Although the process may sound sequential, in reality this work is extremely dangerous. Shipbreaking workers often work 12 to 16 hours a day, earning only about $3 to $4. They face the risk of falling steel, slipping from heights, explosions caused by residual oil, or inhaling asbestos dust, a substance that can cause permanent lung damage. At many shipbreaking yards, protective equipment is scarce and access to medical care is limited. Since the late 1960s, nearly 2,000 serious accidents have been recorded, and the actual number may be much higher, as many migrant workers are not officially documented. Many international organizations have made efforts to improve working conditions, but change has been slow. Shipbreaking remains an industry that relies more on human labor than machinery, and that reality keeps the risk of accidents ever present. Outside the shipbreaking yards, many workers live in makeshift housing, lacking clean water and basic sanitation. The physically demanding yet unstable nature of the work limits their access to education, insurance, and alternative livelihoods, forcing many to remain tied to a highly dangerous occupation for years. What has allowed this industry to exist for more than half a century is the enormous economic value of recycled steel. When a ship is cut apart piece by piece, every steel plate, every pipe section, and every structural frame becomes a resource. A medium-sized cargo ship can supply 10,000 to 25,000 tons of steel, while a large cruise ship can exceed 40,000 tons. All of this steel is sent to furnaces to be reborn, becoming billets, rebar, steel plates, and countless products used in construction, bridges, roads, and infrastructure. The environmental benefits of recycled steel are also significant. Recycling saves up to 70% of the energy compared to producing steel from ore, while also reducing CO2 emissions. Beyond steel, other metals, such as copper from electrical wiring, aluminum from railings, brass from propellers, and stainless steel from industrial kitchens, are recovered at high rates. These materials have long service lives, and reusing them helps reduce pressure on natural resources. Even many mechanical components, such as compressors, generators, pumps, and navigation systems, are inspected and resold to local markets. From a ship that appears to have lost all value, the shipbreaking industry can generate millions of US dollars in materials and equipment, allowing them to continue their journey in new projects. Shipbreaking is often described as a victory for recycling in the circular economy. Steel is recovered, resources are conserved, and global emissions are reduced. But the environment is not always saved. Sometimes it dies somewhere else. At shipbreaking yards, the price paid is no longer abstract numbers, but soil, water, air, and human lives. A single ship contains dozens of hazardous substances: asbestos in piping, lead-based paint on the hull, PCBs in electronic equipment, heavy metals, residual oil in tanks, and even biological waste from cruise ship sanitation systems. If not handled carefully, these substances can seep into the soil or flow into the sea, causing contamination that can last for decades. In many areas near shipbreaking yards, concentrations of heavy metals have been found to far exceed permitted levels. Fish and marine life declines sharply, land becomes degraded, and local residents face serious health problems. The beaching method, though cheap and widely used, causes significant environmental damage because the entire process takes place on open beaches, without proper waste treatment systems. In a city packed with more than 9,000 high-rises, more towers than some entire countries, Hong Kong hides a paradox that still shocks engineers around the world. Its skyscrapers are built using bamboo. Not steel frames, not cutting-edge materials, but over 5 million bamboo poles woven every year around the exteriors of towering buildings, forming a giant wall suspended in midair. These seemingly fragile poles wrap around multi-billion-dollar structures and tremble in the wind, as if a single mistake could spark a devastating disaster. So why would one of Asia's most advanced financial hubs put its trust in a material that's flammable, lightweight, and looks outdated? The bold story behind that choice is something you won't be able to look away from. Few people realize that one of China's most enduring resources comes from a hollow plant. Over 7 million hectares of bamboo forests stretch across the country like a giant green carpet. Not only a symbol of Asian culture, but also a $60 billion a year industry that many nations can only dream of. But bamboo's story goes far beyond its economic value. From old riverside houses and wooden bridges linking village to village, to scaffolding built entirely by hand for thousands of years, bamboo has been the backbone of countless structures long before humanity ever invented steel or concrete. With its flexible yet strong fiber structure, it can withstand storms, high winds, and even survive across generations. Yet bamboo's journey doesn't end in the past. In a city packed with skyscrapers like Hong Kong, bamboo still plays a vital, irreplaceable role. Quiet, but essential. And it wasn't until the devastating fire of 2025 shocked the world that a hidden truth finally surfaced. Why bamboo has survived in modern construction for hundreds of years. The disaster began on the afternoon of November 26, 2025, at the Wang Fuk Court Housing Complex in Taipo. It started with just a small spark that caught the protective mesh in the bamboo scaffolding, and within seconds, everything spun out of control. 12 seconds later, the entire bamboo frame ignited as if it had been soaked in fuel, swallowing the building's exterior and turning it into a fire column hundreds of meters tall. Inside, residents were trapped in thick black smoke and unbearable heat. Hallways glowed red, stairwells went completely dark, and burning bamboo rained down like fireballs, making it nearly impossible for rescue crews to get close. The alarm level was raised to level 5, the highest. More than 60 fire trucks battled throughout the night, but the flames clung tightly to the dry bamboo, rendering every effort almost useless. When the fire finally died, Hong Kong was left in heavy silence. 94 people dead, dozens injured, and hundreds evacuated in the middle of the night. And in the smoldering aftermath, one question echoed across the entire city. Why was such a flammable material used to wrap the exterior of skyscrapers in the first place? To understand why bamboo is still trusted today, you have to look at how it's actually built. Something far more surprising than most people expect. Behind the familiar sheets of fabric covering Hong Kong's skyscrapers lies a construction world almost no one sees except the scaffolders themselves. Every bamboo structure rising dozens of stories begins with just two simple materials: thick bamboo poles for the main load, and thinner ones for reinforcement, woven together like the skeleton of a giant creature clinging to the building. No bolts, no forged steel, only plastic ties pulled tight by hand, forming perfect grid patterns strong enough to withstand the winds that whip through narrow city streets. Layer after layer is added from the ground all the way to the rooftop without any heavy machinery. Becoming a true bamboo scaffolder takes 3 to 5 years of training, learning how to climb, tie, balance, and even feel the tension of the bamboo through the palms of their hands. From a distance, the whole system looks fragile, but the closer you look, the more you understand how it has survived for a century. A quiet craft that holds an entire city up in the sky. In real construction work, bamboo is seen as the industry's secret weapon, not because of its strength, but because of its almost unbelievable flexibility. When a building needs its windows replaced 200 meters up, a long vertical crack repaired, or a massive billboard weighing tons installed, bamboo is often the only material that can wrap perfectly around any shape of a structure. While steel scaffolding requires precise joints and can take weeks to assemble, bamboo can bend, twist, and grip onto every corner in just a few hours. In alleyways so narrow that trucks can't even back in, scaffolders simply carry the poles by hand up each floor and build the framework right on the spot, something no metal system can do. With bamboo, the city gains an extra temporary backbone, so flexible and alive that you almost forget it's just a hollow plant. At 30 stories up, bamboo stops being just a material. It becomes fate. Every scaffolder knows they're standing on poles no thicker than a wrist, tied together with knots they have no choice but to trust completely. One strong gust of wind is enough to make the whole frame tremble like their own heartbeat. What most people don't realize is that for bamboo to even reach this height, it goes through a strict life cycle. 3 to 5 years of growing, 3 months of sun drying, and it can only be used a maximum of 3 times. But no matter how carefully the poles are selected, humans remain the weakest link. Every year there are slips, poles that snap without warning, and tiny accidents so quick they're almost invisible, yet enough to take a life in seconds. Not as loud or dramatic as the 2025 fire, these tragedies happen quietly. But they reveal the constant danger hiding behind every single bamboo pole. So if it were you, would you dare to stand at that height for about $18 an hour? After everything we've seen, all the risks, all the close calls, you'd think bamboo would have been banned from modern construction. But here's the irony. The very things that make bamboo look outdated are exactly what give it an edge steel or aluminum can't touch. Bamboo walks onto a job site like a silent economic warrior. It's so cheap that any project, from an old apartment block to a $1 million skyscraper, can put up scaffolding without ballooning the budget like metal would. It grows everywhere in southern China. It's light to transport, easy to replace, almost as if it were made for a city that never stops building, like Hong Kong. But what keeps bamboo alive after all these centuries is a kind of efficiency no other material can mimic. It's light as air, letting workers climb, tie, and hang hundreds of feet above the ground using nothing but their own strength. Its flexibility lets it absorb shaking, impacts, and sudden gusts between buildings, moments where steel can sometimes snap. And behind all that is one of nature's own tricks. Bamboo is the fastest growing plant on Earth, stretching up to 60 centimeters in a single night, reaching 40 meters tall, built from long vertical fibers that act like natural cables. That structure makes bamboo harder to snap sideways than steel of the same weight. Once you understand that, you realize bamboo isn't a relic of the past at all. It's a natural solution that modern construction, whether it likes it or not, still depends on. Even though those bamboo scaffolds can wrap around an entire skyscraper, their true soul lies in the people behind them. The workers who have spent their whole lives clinging to the city's facades with calloused hands. They're the few who can feel bamboo with their palms, who can hear the slight bend of each pole, who know exactly where pressure can be placed and which knot must be fixed before the wind changes direction. There was a time when Hong Kong had tens of thousands of men like that. They climbed the scaffolds as if performing a ritual, casually stepping up to the 30th floor in simple rubber slippers, tying knots so fast your eyes couldn't follow. Their names never appeared on construction records, nor were they present at grand openings. Yet they were the first to lay hands on a building and the last to leave after the final frame came down. But this trade demands more than skill. It demands courage. Every step hangs over a height where a single strong gust is enough to tighten a man's chest. $90 a day isn't small money, but it will never truly balance the daily risk that no one can predict. And as Hong Kong grows more modern by the day, these workers remain quietly in the background, keeping every bamboo pole straight, every knot secure, so the city can continue standing tall against the sky. After the 2025 disaster, questions about safety were no longer just debates within the construction industry. They became the driving force behind stricter regulations. Authorities began tightening standards, requiring material inspections, supervising every joint, and clearly defining where bamboo scaffolding could still be used. In the new urban landscape, steel and modern modular scaffolding systems are gradually taking over in financial districts, commercial zones, and new high-rise projects, places that demand fast progress, international standards, and uniform load-bearing capacity. With 3D modeling, facade inspecting drones, and wall climbing robots supporting construction, many contractors are beginning to envision a future less reliant on traditional materials. Even so, bamboo hasn't disappeared. Its low cost, lightweight, and unmatched adaptability to the twisted, irregular surfaces of older buildings give it a unique place in the city. In narrow alleys where trucks can't enter, or on decades-old structures with complicated facades, bamboo remains the only material that can truly hug the shape of Hong Kong. In the next 10-15 years, the city will likely witness a quiet transition, steel scaffolding rising with the new skyline, and bamboo holding onto the old streets, where history and modernity briefly stand side by side on the same facade. As Hong Kong stands between two choices, preserving tradition or shifting fully to modern steel scaffolding, a bigger question begins to surface. Where is the future of building materials headed as the environment becomes more alarming by the day? The global construction industry now accounts for nearly 40% of all energy consumption and emits over 2.7 billion tons of CO2 each year, leaving behind a massive carbon footprint no city can ignore. And under that pressure, the world is once again turning its eyes to bamboo, not just as scaffolding, but as a promising green material for the future. Bamboo's journey doesn't end on high-rise scaffolding. Once it leaves the construction site, it steps into a gentler, more delicate role, becoming the small green products we hold every day. To get there, bamboo goes through a kind of transformation. Carefully selected culms are cut down, hollowed and smoothed until they're as clean as the inside of a flute. Inside the workshop, they're dried at 70 to 80 until their natural golden color appears. Then each piece is hand-polished to remove every rough edge, so that when it touches your lips, all you feel is pure simplicity. After being disinfected and dried again at a low temperature, every straw is sorted like a true handcrafted item before being placed into recycled cardboard packaging. Tiny and unassuming as it is, each bamboo straw is a reminder that nature still offers us a way forward, a way to replace single-use plastic, one sip at a time. If bamboo straws are the starting point of a sustainable lifestyle, then bamboo spoons are the next step, where this humble material gets upgraded by technology. After the finest pieces of bamboo are selected, they don't enter a simple manual process. Instead, they go straight into an automated cutting system, where each spoon blank is shaped by high-speed blades. Robotic arms then smooth the curve of the handle, polish the bowl of the spoon, and refine every surface until it feels solid in the hand, yet warm with bamboo's natural touch. Sterilizing and drying take place in sealed chambers to preserve the wood's natural color. And only after passing a final inspection for smoothness and durability are the spoons packaged, sometimes by hand, sometimes by robots, before leaving the factory to become a refined, eco-friendly companion at every meal. Bamboo never stops surprising us, even as it finds its way into the most familiar objects in our daily lives, like the toothbrush we use every morning. Mature bamboo pieces are carefully selected, trimmed, and shaped into gently curved handles that feel warm in the hand, a stark contrast to cold plastic. Once the handle blanks are formed, an automatic drill creates rows of tiny, perfectly aligned holes, ready for the bristles. On another line, a laser etches the brand logo onto the surface, crisp and clean while preserving bamboo's natural color. The bristles, chosen for softness and durability, are then inserted with robotic precision into each slot. Finally, each bamboo toothbrush is packaged in a minimal, sturdy paper box, ready to become a greener alternative to single-use plastic. A small, everyday item, yet one that continues the endless story of bamboo's ability to reinvent itself in a sustainable age. If bamboo toothbrushes show us the material's refinement in tiny details, then in another form, bamboo steps into fire to tell a completely different story, the story of green energy. Inside large kilns, bamboo tubes are stacked upright, leaving small gaps for heat to flow through like the hot breath of a furnace. Once the kiln is sealed, with only a few vents left open, the entire chamber becomes a closed reaction vessel where temperatures of 600–700 degrees are held for 5 to 7 days. In that dense darkness, the cellulose and lignin slowly break down, leaving behind a glossy black carbon core, the soul of bamboo charcoal. When the lid is opened, a thin white smoke drifts out, revealing smooth, solid, evenly colored charcoal, the sign of a perfect carbonization batch. Each kiln produces about 2 to 3 tons, which are then crushed or kept whole and packed in eco-friendly craft paper bags. From cooking fuel and water filters to deodorizing and cosmetics, bamboo charcoal proves one thing: the journey of bamboo doesn't end on scaffolds or dining tables. It keeps finding its way into modern life. Over a month of meticulous labor goes into creating a single sheet of paper, just a few thousandths of an inch thick, a craft that Chinese artisans have preserved for thousands of years. This seemingly fragile paper can last more than 3,000 years without decaying. Have you ever wondered why, in an age of machines and automation, they still remain faithful to such a complex process? Today, let's step inside the largest handmade paper workshop in China to uncover what amazes the world, why these delicate sheets can cost up to $22 each, and how something as simple as paper became a cultural treasure of timeless value. Finishing a single sheet of handmade paper demands more dedication than most modern factory jobs. Inside today's fine art workshops, consistent techniques make it possible to produce between 100 and 300 sheets in one day. Yet in remote craft villages, that output drops dramatically, rarely surpassing 60. Even a seasoned papermaker with steady rhythm and favorable weather typically completes only 50 to 60 sheets after a full day of work. In truth, the journey of one sheet alone can stretch across 1 to 3 days, shaped by the fiber's character, its thickness, and the air's humidity. Each phase requires calm focus, practiced precision, and a sense of timing. That is why every handmade sheet carries more than texture or form. It holds the imprint of time, the quiet endurance of human effort, and the lasting spirit of craftsmanship passed from one generation to the next. Although each region turns to its own natural sources, the making of handmade paper always opens with the same essential act: preparing the fibers. In Japan, craftsmen favor the inner bark of the paper mulberry tree, called kozo. Nepalese papermakers use daphne or lacca, while Chinese artisans depend on young bamboo stalks. Across Europe, the tradition draws from straw, flax, and even discarded cotton and linen, taken from old textile mills. Whether gathered from forests, farmlands, or factory remnants, every raw material shares one defining quality: a high concentration of cellulose. After harvesting, the bundles are tied and laid under the sun to dry, reducing both moisture and resin. In certain regions, artisans even collect bark that naturally peels away from trees to preserve the fiber's length and strength. When fabric is used, preparation begins with sorting, cutting, and soaking to soften the cloth before it is boiled in a mild alkaline bath that removes oils and impurities. The details change depending on the material. Bamboo and straw must be chopped into fragments before boiling. Kozo bark is scraped to clear the dark outer skin. Hemp is rinsed for days in flowing water to remove sap, while old rags are pounded repeatedly until they become soft and cloud-like. After the fibers have been cleaned and organized, they move into the steaming phase, a key operation that softens the raw material and releases the cellulose inside while preserving its natural integrity. Bundles of kozo bark, tender bamboo, or hemp strands are arranged in broad wooden tubs or metal steamers, then subjected to a balance of heat and moisture for several hours. The intense temperature loosens the exterior layers, separates them from the fiber's core, and draws out resins, oils, and bitter plant compounds. For dense materials like bamboo or straw, the steaming may last many hours until the fibers become flexible enough to peel. By contrast, kozo bark needs far less time, typically 30 to 60 minutes, just sufficient for the dark outer coating to soften and detach. This step makes it possible for artisans to lift away the surface layer and expose the pale, silky fibers beneath. No synthetic agents are used here. Steam and water alone complete the transformation. Thanks to this gentle approach, the fibers retain their natural resilience, strength, and clarity. When the steaming is done, left to cool at room temperature, and then rinsed thoroughly to prepare for the next stage of papermaking. Once the fibers have been softened by steam, the artisan begins the intricate work of peeling, a process that relies as much on intuition as on precision. The bark is taken out of the steamer while it's still warm, at the moment when the dark outer skin has loosened from the pale layer beneath. With a slender knife or a finely sharpened bamboo blade, the craftsman moves along each strip in smooth, deliberate strokes. For materials such as kozo or lacca, this careful motion separates the softened bark and exposes the white inner fibers, known as bast fiber, composed almost entirely of cellulose, the key to paper's strength and flexibility. Once the peeling is complete, the white bark is washed repeatedly in clean cold water, often sourced directly from natural streams. The low temperature helps remove sap, dust, and lingering traces of impurities. In traditional workshops, mountain spring water is favored for its purity and low mineral content, which keeps the fibers soft and prevents any yellowing. By the end of this stage, the bark turns a gentle ivory shade, a subtle signal that the material is now clean, elastic, and ready to move forward on its journey toward becoming handmade paper. The freshly peeled bark, or separated fibers, are then laid out in thin, even layers to air dry, an important step that removes excess moisture before the boiling stage. This drying period generally lasts between 4 and 8 hours under mild sunlight, or up to 2 days when the air is damp and overcast. Artisans prefer open courtyards with gentle airflow, where the breeze moves freely, but the warmth stays moderate, allowing moisture to evaporate slowly, without making the fibers brittle. When perfectly dried, bundles of kozo or lakta develop a soft ivory hue and give off a faint, earthy scent. During humid or rainy days, the material is carefully moved indoors, where controlled warm air or light charcoal heat is used to maintain a steady drying pace and preserve the fiber's natural texture. Once the fibers are completely dried, the artisan moves on to the boiling phase, the key step that unlocks the plant's inner structure and prepares it for transformation. Clean bundles of bark, straw, or fabric scraps are placed into a large vessel filled with a gentle alkaline solution. As the temperature rises slowly, natural binders such as lignin and hemicellulose begin to break down, loosening the connections between fibers and making them more pliable. It's the moment when the plant's inner threads are released, exposing the pure white cellulose core, the true foundation of paper itself. Depending on the raw material, the boiling time ranges from 2 to 4 hours. Tougher fibers like straw or bamboo take longer to soften, while kozo and lakta reach the right texture in roughly 2 hours. When the liquid turns a pale yellow and the fibers can be gently pulled apart without breaking, ready to move on to the next chapter in the paper-making journey. After boiling, the entire mass of softened fibers is transferred into clean water basins for the next step, removing impurities. Using their hands or fine bamboo tweezers, artisans patiently extract every small remnant of bark, dust, burnt pieces, or wood splinters left behind from the cooking stage. This careful inspection is done entirely by hand, since no machine can identify the difference between strong, usable fibers and weak, damaged ones with such precision. In traditional Japanese paper-making studios, the fibers are often spread out on wooden trays under natural daylight, so that every imperfection becomes visible. Only the long, even, and spotless strands are selected for the next step. The rest are either discarded or saved for recycled paper. Once the fibers are fully cleaned and sorted, craftsmen begin the beating process, the phase that softens, separates, and refines each strand. Each rhythmic strike, driven by hand or by a simple foot-powered device, forces the fibers to collide, loosen, and soak up water until they grow soft and elastic. In contemporary paper-making studios, this demanding manual step has largely been replaced by the Hollander beater, a machine fitted with a rotating drum lined with metal blades that stir the fibers continuously in water. Despite the change in tools, the goal remains identical: to separate and refine the fibers without breaking them apart. When the process is done properly, the pulp develops a smooth, silky texture and stays evenly suspended in water. Once the fibers have been thoroughly beaten, the papermaker begins preparing the pulp, a delicate blend that determines the sheet's final quality. The softened, silky fibers are transferred into a wide vat filled with clear, fresh water. The cleanliness and neutral pH of this water are essential, as they influence both the paper's feel and its long-term durability. Into this vat, the artisan adds a thick, slippery extract from the roots of the Tororo aoi plant, called neri. This natural mucilage works as a mild binder, helping the cellulose fibers stay evenly suspended throughout the mixture instead of settling at the bottom. With slow, controlled motions, the papermaker stirs the vat using a wooden paddle until every strand is evenly distributed. When the pulp mixture reaches the ideal balance between smoothness and dilution, the papermaker proceeds to the most defining step of all: sheet formation. Using two essential tools, a bamboo or finely crafted wooden mold and a supporting frame, the artisan gently dips the screen into the vat of pulp, then moves it in steady, rhythmic motions. Each shake, forward and side to side, helps the fibers disperse evenly across the surface. What appears to be a simple motion is actually a skill refined through years of experience. Every movement guides the fibers to interlock naturally, forming a thin, web-like structure. This interwoven network is what gives handmade paper its extraordinary durability and resistance to tearing, a strength no industrial paper, bound by synthetic adhesives, can truly replicate. In larger studios, entire rows of artisans stand shoulder to shoulder along vats, stretching dozens of feet, moving their molds in unison. Their synchronized rhythm sends soft ripples across the surface, a mesmerizing choreography unique to this ancient craft. After several seconds, excess water drains through the mesh, leaving behind a delicate, uniform layer of pulp. The papermaker then lifts the mold, lets the remaining droplets fall, and transfers the wet sheet onto a smooth surface or a felt pad. Each new layer is stacked carefully atop the last, demanding absolute concentration, for even the slightest imbalance in movement can lead to uneven fiber patterns or weak spots in the finished sheet. Immediately after the sheet takes shape in the vat, the papermaker transitions to the pressing phase, an essential step that expels excess water and binds the cellulose fibers into a unified structure. Each freshly formed sheet is stacked one over another, creating a thick, even pile. Once the desired number is reached, the stack is transferred into a wooden or hydraulic press, where steady downward pressure squeezes the trapped moisture from between the layers. In traditional studios, this task is often performed manually with a lever-operated press that depends on gravity and balance rather than mechanical power. The pressing can last anywhere from 30 minutes to several hours, depending on the paper's thickness and the room's humidity. But this step does more than remove water. It tightens the fibers, enhancing their natural adhesion and reinforcing the integrity of each sheet. The outcome is a dense, well-bonded layer of handmade paper. Its strength earned through pure mechanical force, not through synthetic glues or chemical binders. Once the sheets have been pressed and most of the water expelled, they remain damp and flexible, ready for the drying phase. In traditional papermaking studios, artisans gently peel each wet sheet from the felt and lay it face down on flat drying surfaces such as wooden boards, metal panels, or specially designed walls. Each sheet is carefully smoothed by hand to remove air pockets, ensuring that it will dry flat without curling or warping. Depending on the paper's thickness and the surrounding weather, drying can take anywhere from several hours to an entire day. Modern studios often rely on controlled drying rooms, where the temperature stays between 85 and 100 degrees Celsius and gentle air currents circulate constantly. This environment helps the sheets dry evenly while preserving their natural tone and texture. Still, many craftsmen favor sunlight drying, long considered the gold standard, as natural light imparts a warm ivory hue, enhances the grain of the fibers, and creates a smooth tactile surface. Once fully dry, each sheet is carefully lifted, stacked, and given a final pressing under heavy wooden boards. The result is a light yet durable handmade paper, defined by its unique fiber patterns, a quiet mark of human craftsmanship that no machine can truly imitate. After every sheet has been thoroughly dried and flattened, the papermaker enters the final phase, quality inspection. Each sheet is lifted toward natural or directed light, allowing the artisan to study its thickness, fiber alignment, and any minor flaws, wrinkles, thin patches, or traces of uneven fiber layering. The highest grade sheets reveal a uniform tone, a smooth surface that still shows the subtle grain of the fibers, and a touch that feels both delicate and strong. Any sheet that fails to meet these standards is carefully set aside and repurposed, often used for craft work, gift wrapping, or recycled into the next batch of pulp. Those that pass inspection are pressed one final time to achieve flawless flatness before being stacked and packaged by hand. At this point, the handmade paper is ready to be sent to printers, runt artists, and artisans who transform it into journals, lamps, calligraphy scrolls, and works of art. It marks the completion of a remarkable journey into resilient, elegant sheets that carry the unmistakable imprint of human craftsmanship. Every year, more than 125 million tons of bananas leave tropical plantations to feed billions of people. But few realize that this entire system relies on just a single banana variety on the planet. And the worrying part is, this variety has almost no natural defense against disease. In recent years, a soil-borne fungus called Panama TR4 has quietly spread across multiple continents, wiping out thousands of hectares of plantations in a short time. If it continues to spread, one of the most familiar fruits on supermarket shelves worldwide could disappear faster than we expect. But instead of accepting that risk, scientists, export plantations, and even the global cold chain logistics system have been forced to change the way bananas are grown, protected, and transported. So what is actually keeping this multi-billion-dollar banana industry from collapsing? Bananas first appeared in Southeast Asia around 7,000 years ago, before spreading along ancient migration routes to Africa, where they quickly became a staple food for tens of millions of people in East Africa, a role they still hold to this day. Today, bananas are grown in more than 130 countries worldwide. Among them, India is the largest producer, with over 37 million tons each year, mostly for domestic consumption. But when it comes to exports, the true center of the global banana industry is Ecuador, which supplies about 7 million tons annually, nearly 30% of the world's total banana exports. Thanks to their low cost, high energy content, and ability to be transported over long distances, bananas have become the most consumed fruit in the global supermarket system, while also providing a direct livelihood for more than 400 million people across tropical regions. However, the global banana industry nearly collapsed in the 1950s when a fungal outbreak known as Panama disease almost wiped out the dominant export variety at the time, Gros Michel, across Central America. Within just a few decades, hundreds of thousands of hectares of plantations were abandoned, forcing the entire global production system to switch to a single replacement variety, Cavendish. And now, as a new strain of the fungus, Panama TR4 has reached Latin America, the world's main banana export hub. More than 80% of the global export banana supply is under threat. Because of that threat, Ecuador has been forced to control banana cultivation from the moment young plants have not yet left the nursery. Today, bananas are almost never grown from seeds. Instead, plantlets are produced through tissue culture in laboratories, then planted in rows with a standard spacing of about 2 to 3 meters between each plant, ensuring proper airflow and slowing the spread of soil-borne diseases. From the earliest growth stages, soil moisture is carefully managed using drip irrigation or low-pressure spraying systems, typically supplying around 25 to 40 millimeters of water per week per hectare. This helps maintain a stable environment for root development without creating favorable conditions for fungal outbreaks. At the same time, a strict crop protection schedule is maintained. On large-scale plantations, fungicides and insecticides are applied regularly, often between 20 and 40 times per year. In many cases, agricultural aircraft fly directly above the banana canopy, creating an almost continuous protective layer across the entire field. Because Panama TR4 can survive in soil for decades, many plantations have also introduced strict biosecurity measures. These include disinfecting vehicle tires at entry points, limiting worker movement between planting zones, and monitoring each plantation area using digital disease mapping systems. Around the 7th month after planting, a large purple flower begins to emerge from the top of the banana plant, a clear sign that a bunch of fruit is starting to form. At this stage, farmers cover the entire flower bunch with specialized bags to protect the young bananas from insects, harsh sunlight, and strong winds, while also helping the fruit grow evenly and maintain the skin quality required for export. However, the protection process does not stop there. To prevent the plant from wasting nutrients on unnecessary parts, farmers remove the small flower tips at the end of each banana, then cut off the purple tail at the bottom of the bunch. A small step that helps concentrate all the plant's energy on the fastest growing fruit. After that, the banana bunch is sealed once again with protective covering to maintain a stable layer of protection throughout the entire development stage. Over time, banana bunches that have been protected and managed through multiple layers of control begin to grow rapidly beneath the dense canopy of the plantation. Once each fruit reaches the export standard size, the entire growing area immediately moves into the harvesting stage, a process that requires near-perfect precision to preserve the quality of every single bunch. This process is typically carried out by 2 workers working in close coordination. One holds the plant to control the direction it falls, while the other uses a sharp knife to cut the bunch stem at a point about 20 to 25 centimeters above the last hand, the necessary length to attach it to the plantation's internal transport system. Almost immediately, the heavy bunch, which can weigh up to 50 kilograms, is carefully supported on a padded shoulder to prevent scratches or bruising. Even a small mistake within those few seconds can cause the entire bunch to lose its export value. For this reason, in the global banana production chain, Harvesting is not a simple final step, but a critical stage that determines the quality of everything that follows. Once cut from the plant, the journey of the banana bunch is far from over. Immediately after being lowered from the worker's shoulder, it is hooked onto overhead cable lines positioned about 1.5 to 2 meters above the ground, connecting the harvesting area directly to the processing facility. With pulleys and directional switches placed along the route, these banana trains can quietly travel several kilometers beneath the tropical canopy with almost no damage or scratches to the fruit's surface. This system has almost completely replaced traditional manual transport methods, such as using horses or carrying loads by hand, significantly reducing labor effort while maintaining fruit quality throughout the journey. While a conventional truck can carry only about 35 to 40 banana bunches per trip and depends heavily on flat terrain, an internal plantation cable system can transport up to around 90 bunches at the same time, operating efficiently even across steep slopes, muddy ground, or plantations that remain wet year-round. When the last banana bunches are taken away, the mother plant has fulfilled its only purpose, because bananas are plants that flower just once, to prevent pests and diseases, and to make room for the next generation growing from the base. The trunk is shredded on site by chopper machines, returning nutrients to the soil in a quiet but complete cycle. However, not everywhere does the banana plant end its life this way. In countries such as India, the Philippines, and Vietnam, the remaining pseudo-stem after harvest is often kept to extract fiber, a natural biomaterial with a commercial value of about $300 to $600 per ton of raw material. After the mother plant is cut down, the thick, cellulose-rich outer layers of the pseudostem are separated from the soft inner core to retain the strongest fibrous structure. This material is then processed through mechanical extraction systems that pull it into long, continuous fiber strands, while still maintaining the plant's natural moisture. These raw fiber strips are then washed to remove plant sap and surface impurities. As excess moisture is reduced through natural sun drying, the fiber structure stabilizes and its tensile strength increases significantly. In the final stage, the dried fibers are twisted into light but durable threads, strong enough to withstand weaving and further processing. From there, they become raw material for products such as mats, handicraft bags, and various high-value bio-based materials for export. Time is a critical factor for bananas. Within about 4 hours after leaving the plant, the banana bunches must arrive at the packing facility to preserve maximum freshness and prevent early ripening from starting. At this stage, the protective bags used in the field are removed, revealing fresh green banana bunches still covered with dirt and plant sap after their journey through the plantation. Their first stop is a preliminary washing system, often described as an artificial rain, where continuous cold water sprays remove mud and impurities while also lowering the fruit's surface temperature to slow down its natural respiration process. After this initial cleaning, the banana bunches move to the central processing area. Here, workers quickly separate the large bunch into smaller hands using precise and decisive movements, preparing them for the next sorting stage. The banana hands are then placed into specialized cleaning tanks, where they are soaked for a controlled period to remove remaining sap and reduce the risk of fungal growth during long-distance transport. In the following stage, the banana hands are divided into smaller uniform clusters, typically weighing around 700 to 900 grams, matching export packaging standards. These clusters are immediately transferred onto conveyor belts for traceability labeling and final inspection before entering the boxing line. Throughout this entire process, low-pressure spray systems continuously wash away any remaining solution on the fruit surface while maintaining a stable temperature after treatment. This step is essential to preserve the banana's uniform green color before they enter the packaging stage and begin their cold chain journey across the ocean. Not all bananas continue their journey as fresh fruit. A portion of them becomes raw material for the food processing industry, especially for the production of export banana chips. After cleaning, the bananas are transferred to the peeling area, where skilled workers can handle between 400 and 600 fruits per hour, with fast but highly precise movements. This step is critical because even a small scratch can cause the slices to curl or burn during the frying process later. From there, the bananas are fed into high-speed industrial slicing machines, where the blades are pre-adjusted to produce uniform slices of about 3 millimeters thick. This thickness is optimized so the outer layer becomes ideally crispy when fried, while the inner core still retains a firm texture and the natural sweetness of green bananas. Immediately after slicing, the banana pieces pass through a light washing conveyor to remove excess starch from the surface. They are then pre-dried at around 60 to 65 degrees Celsius to dry the outer layer and stabilize the structure of each slice. This step helps preserve the natural flavor before the slices are placed into the frying oil. The slices are then fried in oil at a temperature of about 160 to 180 degrees Celsius for 2 to 4 minutes to create an even crispy layer without losing their natural flavor. The temperature is tightly controlled to avoid burning the outside or causing excessive oil absorption. This step directly determines the crispness, color, and aroma of the final product. After that, they are coated with flavorful seasoning and immediately transferred to an automated packaging line, which can process around 8,000 to 10,000 packs per hour depending on package size. Each pack is precisely portioned, air-sealed to preserve crispness, and tightly sealed to maintain quality during long-distance transport. Finally, the packaged products are labeled with traceability codes and arranged onto export pallets, ready to leave the factory for supermarket shelves or to travel across oceans to markets around the world. Traceability allows full control over the product's journey from raw material to the end consumer. The pallets are then wrapped and loaded into refrigerated containers to maintain quality throughout transportation. If green bananas are used to make crispy snacks like chips or fried products, ripe bananas serve a completely different role. When the peel turns a bright yellow color, the starch inside has been converted into natural sugars, while the levels of vitamin B6, vitamin C, potassium, and fiber also reach an ideal level for the human body. Thanks to their easily digestible energy and mild sweetness, ripe bananas have become one of the most commonly consumed fruits on the tables of billions of people every day. Not only humans, but many wild animals also depend on bananas as an important food source. Monkeys, elephants, forest birds, and fruit bats are strongly attracted to the distinctive aroma of ripe bananas. As they eat, they unintentionally carry seeds and spread them across different areas of the forest, helping maintain the natural ecological cycle of tropical ecosystems. For this reason, ripe bananas not only feed humans, but also quietly connect and sustain the lives of many species. But the most important thing about bananas is not their taste or convenience. It lies in the silent role of the entire system behind them. Every year, the world consumes more than 400 billion bananas, and for hundreds of millions of people in Africa, South Asia, and Latin America, bananas are not a snack. They are a daily staple food. If bananas were to disappear within just a few years, the impact would not stop at supermarket fruit shelves. Millions of hectares of plantations would be abandoned. Millions of agricultural workers would lose their livelihoods, and the supply chain of affordable food for many developing countries would be immediately disrupted. Tropical ecosystems that depend on bananas as an intermediate food source for many animal species would also be affected. That is why today's precision farming techniques, strict disease control systems, and strategies to protect banana varieties are not just about increasing production. They are about safeguarding one of the most critical food links on the planet. Before humans redrew the map of North America, bison were the dominant species across this land. Tens of millions moved like a living current, helping shape soil structure, regulate vegetation, and create the conditions for biodiversity to develop. But in less than a century, bison were nearly wiped out by humans. As they disappeared, the grasslands began to decline. Areas that were once green gradually became dry and ecologically unstable. More than 100 years later, a bold experiment was carried out, returning bison to degraded lands. The results showed clear signs of recovery in just about a decade, as entire ecosystems gradually began to rebuild. In today's video, Mandarin Tech explores the return of the bison, a species once on the brink of extinction, yet one that may change the ecological future of North America. Before Europeans arrived, North America was a continent that possessed one of the largest grassland ecosystems on Earth, a vast prairie belt stretching from southern Canada all the way to northern Mexico. Covering millions of square miles, it was more than just grassland. It was the biological foundation that sustained an entire continent. Within that ecosystem, bison played a central role. Their herd movements, trampling, and cyclical grazing created a continuous cycle of impact on soil, vegetation, and nutrient flows, allowing the ecosystem to operate in a stable state over long periods of time. However, beginning in the 16th century, as Europeans expanded westward, this balance rapidly collapsed. In less than 100 years, the bison population fell from an estimated 60 million animals to just a few hundred. This was not only the result of hunting for meat and hides, but also a deliberate strategy aimed at destroying the livelihoods of indigenous communities that depended on bison. When bison disappeared, the grasslands lost their own architect. The land was overfarmed and compacted by confined livestock. Native grasses were replaced by fragile monocultures, causing soil microbial systems to collapse. By the 1930s, these accumulated impacts erupted into the Dust Bowl when topsoil was blown away across vast regions, leaving dead land that persisted for decades. North America was forced to confront a clear truth. Grasslands cannot survive without the very species that created them. At the beginning of the 21st century, many land restoration programs across North America found themselves stuck in prolonged deadlock. For decades, humans had tried every familiar solution: chemical fertilizers, deep plowing, reseeding grasses, even large-scale land modification using heavy machinery. But the results were often short-lived, as the soil quickly degraded once again. In this context, a group of ecologists proposed an idea that ran counter to conventional thinking. Instead of continuing to fix the land from the outside, they asked a different question. What had kept the grasslands stable for thousands of years before human intervention? The answer led them back to bison, a species that had disappeared from much of the North American landscape. Reintroducing bison was not intended as a simple conservation effort, but as a large-scale ecological experiment. Notably, bison were not released into ideal conditions, but into landscapes considered failures: dry, nutrient-poor, and almost entirely devoid of native grasses. To many, this was a risky gamble. No one could be certain that a species once adapted to vast seas of grass could survive on land that was nearly dead. Almost immediately after the bison herd was released, events began to move beyond the researchers' expectations. In the early days, tracking signals showed constant movement, but soon the data became fragmented. GPS collars on several individuals gradually lost signal. Drones flew for hours without capturing clear imagery. Even helicopter surveys detected only faint traces. For weeks, the bison herd seemed to disappear from the tracking maps. There were no carcasses, no clear signs that the animals had left the area, yet no one could confirm that they were still alive. In reality, they were moving toward higher ground, where vegetation was almost non-existent. No one understood why the herd was doing this. Their sudden disappearance meant the entire project was on the brink of collapse. More than $10 million in research at risk, and around 250 scientists facing the loss of their jobs. It threatened to derail what was considered the most ambitious ecological restoration effort in decades. But to understand why the bison behaved this way, we need to look at the very nature of the species. Bison are not animals that adapt through complex learning or flexible behavior like some primates. Instead, they possess a survival instinct refined over tens of thousands of years. When living in a safe environment, they reveal a completely different side: curious, observant, almost like a child discovering the world for the first time. From their earliest days, bison calves learn to swim, with their mothers always close behind, ready to enter cold water if danger arises. This blend of courage, persistence, herd protection, and quiet curiosity is what makes bison such effective ecological engineers, even though they never intended to become one. In an environment without hunting pressure, bison do not behave like domesticated livestock, instead splitting into small groups and moving into remote terrain. Their apparent disappearance was not a failure, but an ancient survival strategy, one that reactivated ecological processes long forgotten by humans. It was these deeply ingrained instincts that ultimately explained what happened next. The disappearance of the herd was not a warning sign at all, but the earliest signal that the bison had successfully adapted and had begun doing exactly what ecological engineers do best, repairing the land beneath their feet. Unlike cattle, which often linger in one area and compress the soil into hard, lifeless surfaces, bison are in constant motion. They rarely remain in a single location for long. Each step they take gently breaks up the surface, loosening compacted soil and creating tiny channels that allow rainwater to penetrate rather than flow away. Along their routes, bison leave behind dung that quickly becomes a natural fertilizer. Rich in nitrogen, phosphorus, and potassium, it replenishes nutrients that native grasses had been deprived of for decades. These deposits help restart soil chemistry that had long been exhausted. When bison roll on the ground, their nearly 1-ton bodies press shallow hollows into the earth. These depressions trap moisture, catching seeds as they fall and creating small sheltered pockets where new plants can take root. Spread across the prairie, these micro-nurseries function like natural reservoirs, slowing water loss and protecting fragile seedlings. Rolling behavior also strips away dead vegetation, exposing bare soil. Exactly the conditions seeds need to germinate. Many of those seeds arrive carried in the animal's thick fur, transported naturally across the landscape. Crucially, bison never overgraze. Their constant movement leaves patches of land undisturbed long enough to recover and regenerate. Through this repeating cycle, the prairie began to heal. Starting with the very first tracks the herd pressed into the soil. The first changes appeared quietly. After 3 years, small green patches began to emerge across land that had once been considered hopeless. By the 4th year, native grasses returned in force, and by the 10th year, drone footage captured a scene few believed possible. A landscape once close to desert had transformed into a vibrant, living grassland filled with color. As vegetation returned, wildlife followed. Bird species absent for 20 to 30 years began to reappear. Pollinating insects came back, along with many small mammals. Soon after, predators such as foxes, coyotes, and bobcats started to reestablish themselves in the area. The soil began retaining moisture more effectively. Streams that once dried up during the summer now held water for longer periods. It was as if the ecosystem had remembered how it once functioned when bison were present, and had begun restoring itself, guided by processes shaped over thousands of years of evolution. Long-term research at the Kanza Prairie in Kansas shows that in areas where bison were present, plant species richness increased by up to 86% over more than 3 decades. Meanwhile, areas grazed only by cattle saw increases of around 30%, while regions without any grazers were the least diverse of all. These findings demonstrate that the ecological role of bison cannot be replaced by any other species. Even cattle, despite their similar appearance, cannot generate the same effects, as they tend to remain in one place for too long, compacting the soil, breaking its structure, and accelerating erosion. Across North America, regions where bison have been reintroduced are now expanding. The Tallgrass Prairie Preserve in Oklahoma, once a cattle ranch, has become the largest restored tallgrass prairie in the world. Its bison herd has grown from just 300 individuals to nearly 2,000. In Montana, the American Prairie Project aims to establish a wildlife corridor spanning more than 3.2 million acres, supporting a population of around 10,000 bison. In Mexico, where bison had completely disappeared since the 19th century, a herd reintroduced from just 23 individuals in 2009 has now grown to more than 200, helping revive the entire Janos grassland. In many regions, including Illinois, abandoned industrial zones have also been transformed back into prairie ecosystems following the return of bison. In reality, not every landscape can simply release bison and wait for a miracle. Many regions also require fire, because fire was an essential component of prairie ecosystems for thousands of years. In Oklahoma, land managers burn roughly 1/3 of the reserve each year to mimic natural conditions. Fire removes dead vegetation, triggers strong regrowth of young grasses, and creates ideal food sources for bison. When bison and fire operate together under this ancient ecological pattern, the prairie revives far more powerfully than through any artificial method. Data collected after 10 years of bison reintroduction shows soil moisture increasing by 25 to 40% after rainfall, erosion decreasing by nearly half, and plant species richness rising by 70 to 80%, depending on the region. Remarkably, areas that had once lost nearly all vegetation have now become hotspots of biodiversity. What is most striking is that no technology, no irrigation systems, and no artificial fertilizers were behind this transformation. Everything was achieved simply through the presence of bison and the natural processes they have followed for thousands of years. The success of bison restoration projects raises a larger question. What would happen if millions of bison, like those that once roamed the continent, were allowed to return across North America? Could the Great Plains regain their historic form? Could soil erosion, land degradation, and even aspects of climate change be reduced simply by letting nature do its job? What is certain is that bison have accomplished what humans failed to achieve after hundreds of years of soil management. They transformed landscapes once considered dead into living ecosystems. Their return shows that ecological restoration does not always depend on expensive technologies, but on understanding how natural systems function and restoring the missing pieces. Yet the greatest irony lies in the present. Today, roughly 95% of bison exist only as commercial products of the meat industry, while just 5% remain as true ecological engineers, the only individuals still capable of reviving an entire prairie. The bison meat industry in the United States is now worth more than $350 million annually, with demand rising steadily by 10 to 15% each year. This growth is driven by bison's reputation as a high-protein, low-cholesterol superfood. However, this economic value has pushed most bison into industrial farming systems, unintentionally reducing the chances for a species that once shaped an entire continent to recover naturally. The story of the bison is not just the story of a species making a comeback. It is a reminder that in nature, the most effective solutions do not always come from high technology or aggressive intervention, but from restoring the relationships that have existed for thousands of years. In a world facing desertification, climate change, and large-scale land degradation, the lesson of the bison extends far beyond North America. It raises a larger question for humanity. Will we continue trying to control nature, or will we learn to work with it? If you find stories about science, technology, and ecology like this worth sharing, please like, share, and subscribe to Mandarin Tech, where the complex stories of our world are told in a clear, insightful, and inspiring way.